Hello, I'm Chris Hay, Extension Water Management Engineer at South Dakota State University, and I'll be guiding you through this online learning module on operation and management of drainage water management systems. This is the 7th module out of 8 total modules as part of the Drainage Water Management Level 2 training. In developing a management plan for a drainage water management system, we're trying to balance 3 main considerations. The first is the environmental goals for nitrate loss reductions or other environmental goals. The second consideration is the production goals that the producer has for that system. And then finally, the site-specific characteristics that are going to influence how we manage that system. You've seen this in other parts of the training, but drainage water management is one of those practices that allows us to get closer to that golden rule of drainage that Wayne Skaggs coined that says to drain only what is necessary to ensure trafficability and crop production and not a drop more. The primary practice standard governing operation and maintenance of drainage water management systems is Conservation Practice Standard 554 for drainage water management. There will be other practice standards that will apply to the system itself, such as 587 for the water control structure and Conservation Practice Standard 606 for subsurface drain. And since drainage water management should really be looked at in the context of a larger conservation system, there may be a number of other conservation practice standards that will apply to the overall conservation system, such as nutrient management and or practices for reducing runoff and erosion. There are 2 main questions that an operational plan for a drainage water management system attempts to answer. The first is when to raise and lower the outlet, and the second is what depth do we set the boards at. Because each site is unique, each system is unique, and each season or year is going to be a little different, drainage water management should really be practiced in an adaptive management framework. And so if we take a look at what an adaptive management framework looks like, we develop that management plan for the drainage water management system. The producer takes that plan and then goes out and implements it. But as they do that, they should really be evaluating and learning as they go along and paying attention to how that system responds to different management actions. Based on that, then they may need to make some in-season adjustments. And then as we continue to learn about how that system responds to different events, then that may necessitate going back and revisiting the plan and coming up with a revised plan. And then with that revised plan, then we repeat the loop and continue to evaluate and learn as we go along so that we come up with a plan that works for the long term. And so as part of that learning and evaluating phase, some of the things that the producer or their advisor should be paying attention to would be monitoring different rainfall events or snowmelt events and how the water table responds to that in the control structures themselves and in any other points where that's possible. And then watching and learning how the system or crop responds to different events depending on the board settings. That also then includes in the off-season and paying attention to how the system responds and when runoff is generated from different sized events. And then also monitoring how the system responds to changes in board settings. How quickly does the water table respond? How quickly does the system drain when those boards are set up higher and the drainage coefficient is effectively reduced? And then again, adapting as needed to make sure that the system best meets those goals. And so with that background, what this module will cover then is the conventional drainage water management scenario as it's traditionally been practiced, some alternative management scenarios, and then some refinements to those. And then finally, some other management considerations that ought to go into drainage water management planning and operations, including addressing some of the frequently asked questions regarding drainage water management. Regardless of the scenario, an important concept to remember is that drainage water management only manages the drainage. It doesn't manage the water table itself. And so the actual water table then is going to be a function of the precipitation that's received, along with evapotranspiration and other losses, as well as the outlet setting. The exception, of course, is sub-irrigation, where we add water back into the system in order to maintain a water table. And that's something we'll discuss briefly later on in the module. If we start with the conventional management scenario, though, there are 3 main modes that we use to operate that system. The first of these modes, then, is winter conservation mode. And so from the time period following fall operations until sometime in the spring before spring operations begin, the outlet is raised up near the soil surface. So this then minimizes drain flow and then also minimizes any nitrates that would go with that drain flow. In order to maximize those water quality benefits, the current recommendation would be to raise that outlet to within 6 inches of the lowest point within the control zone. And then in the spring, generally 2 to 4 weeks before field operations are expected to begin, the boards would be pulled out and the system would be allowed to drain out such that those operations could begin in a timely manner. Note that if the boards are pulled too quickly, it is possible to exceed the flow velocity safe limitations from Conservation Practice Standard 606 for subsurface drains. Ideally, the boards would be pulled slowly over a few days or at least several hours to avoid excess flow velocity in the system. However, in reality, most producers aren't willing to wait that long in pulling the boards. Again, the potential problem with pulling the boards too quickly is developing excess flow velocity in the pipe, which could lead to blowout of the tile. Therefore, there is a recommendation and a requirement in some states to have 20 feet of solid pipe both above and below the control structure, such that excess velocities would be contained within that solid pipe section and prevent blowout of the tile. Depending on the conditions in that spring, the producer may or may not need to pull all the boards, and so if it's not an overly wet spring, it is possible to leave some boards in for some water conservation. Following the completion of spring operations and allowing some time for some initial crop and root development, boards can be placed back into the control structures in summer conservation mode. And then with some timely rainfall, we build in the potential to capture and store and conserve some water for use by that crop. The depth at which we set the boards is going to be a function of soil type, crop, and then also the management effort that the producer is willing to expend. There'll be less capillary rise in a coarser textured soil versus a finer textured soil, and so that allows for a little higher board setting in that coarser textured soil. And of course, the crop's rooting depth and its tolerance for a potentially shallow water table also comes into play in determining that board setting. And finally, the shallower depth at which the boards are set, the more the drainage effectiveness of the system is reduced. And so with the shallower board setting, the producer is going to have to pay more close attention to weather forecasts and rain events, and potentially get out at times of the year and have to pull some boards following some larger events to make sure that there isn't crop damage due to inadequate drainage at those times. Given all those considerations, typical depths for those board settings during the growing season would be 2 to 2.5 feet below the soil surface. And so if we look at how this plays out over the season, looking at the soil profile from the surface down to the tile elevation, again, we start out the season with the boards raised up near the surface from the previous fall to hold back the water, also hold back any nitrate losses over that non-growing season. And then during the spring, 2 to 4 weeks before field operations are expected to begin, those boards will be pulled as needed, potentially all the way down to the tile elevation to let that system drain out and prepare the field for that field work. And following the completion of those spring operations and allowing for the crop to get established, we can then put some boards back into the control structures to potentially try and conserve some water from some timely rain events. In the fall, then, some boards can be pulled if necessary to allow for harvest, but unless it's a wet fall, that may not be needed. Following the completion of fall operations, then, the boards would be set back up to that shallow elevation to reduce drain flow and nutrient loading losses. Those non-growing season periods then represent the potential drain flow reduction, which then also means the potential nitrate loss reduction. And then the period over the growing season where the boards are elevated then represents potential conserved water for that crop. That period also results in some potential drain flow and nutrient loss reductions. Again, keep in mind, however, that those depths are only the outlet depths, and the actual water table is still going to depend on the amount of excess precipitation that we receive in any given year. And so, assuming that we'll need some spring drainage, we'll start that spring with an elevated water table. We pull the boards, allow that to drain out. And then once we put some boards back in the late spring, if we're lucky, we may catch some rainfall that we can potentially store some water from. We may also get a large enough event where we bring that water table up more shallow than we would like, and so that may require pulling some boards in order to to allow for some more drainage to prevent damage to the crop. And then we may or may not need some drainage in the fall. And then again, we put the boards back in following fall operations, and then again, reduce the drain flow and any nitrate losses that would occur with that drain flow over that non-growing season. So now that we've taken a look at that conventional management scenario, let's take a look at a few alternative scenarios. And so one alternative scenario would be one where there is no management during the growing season. And so if the primary concern is just reducing nutrient loading in the off-season, but then during the growing season, the producer's more concerned with having adequate drainage as opposed to trying to conserve some water, or just doesn't want to worry about having to potentially manage control structures during the growing season, this would be a potential scenario for those goals. And so in this scenario, there's still the same potential for drain flow reduction and nutrient loading reductions over the non-growing season, but then the rest of the season would be the same as for conventional drainage. Another scenario at the opposite end of the spectrum would be one with much more aggressive growing season management. In this scenario, the boards are initially set much shallower in summer conservation mode, and then the board settings are changed at one or more times throughout the growing season. This scenario builds in the maximum potential to conserve water over the growing season, but also is going to require considerably more effort. The boards will have to be changed multiple times over the growing season, and then in many years may likely have to go out at times to remove some boards to make sure that there's adequate drainage to prevent crop damage following larger rain events. So while this scenario may sound good in theory, the producer needs to be keenly aware of the management that this scenario is going to entail before adopting a management plan like this. Another management scenario is one for northern climates where freezing of the tile and also of the control structure are a concern. If water freezes up in the control structure, in many cases it may be too late by the time the structure thaws out to get adequate drainage for planting in the spring. In this scenario, it's only that potentially conserved water over the growing season that also is the potential drain flow reduction and nutrient loading reduction. Note that this scenario is not currently covered under the Drainage Water Management Standard. However, because of the concerns of the northern states, it has been an active topic of discussion with the Ag Water Management Group. And now let's take a look at some refinements that can be made to these different management scenarios. One refinement would be for using drainage water management with cover crops. And so if cover crops are used in the off-season, then the board settings, instead of being set as shallow as they would be with conventional drainage water management, instead we would need to lower those board settings at or below the expected rooting depth for that cover crop. In some cases, there may be the potential and desire to create some temporary seasonal wetland habitat using the drainage water management system. And so in that case, the boards would be set very shallow at or close to the soil surface, such that potentially water could be brought up to the surface and fill in some depressions and create some ponded water and some shallow water wetland habitat at times of the year. Another refinement that we've already mentioned is sub-irrigation. And so with conventional drainage water management, at times we may be able to potentially capture and conserve some rainfall by raising the outlet elevation. In many cases, the evapotranspiration demand of the crop is going to exceed the available precipitation, and so for much of the growing season, the water table will drop below the tile elevation. But if we have an adequate water source in a system designed for sub-irrigation, we can add water back to the system to raise and maintain a water table such that we can provide supplemental water to the crop to meet that evapotranspiration demand and increase yield. The details of sub-irrigation are beyond the scope of this training, but I would refer you to Conservation Practice Standard 443, which covers this practice. And then regardless of management scenario, there's a number of other management considerations that go into developing a drainage water management plan. A key management consideration is the level of effort that will be required to manage the system, and also then the level of effort that the producer is willing to put into managing the system. The level of effort required will be a function of the number of control structures within the system, and then also within the management plan, how many anticipated changes to those board settings will be required. Additionally, then, depending on the level of growing season management, what the potential is for having to change boards at times during the season to make sure there's adequate drainage at times of excess rainfall. Use of the buried inline control structures when applicable, or some of the automated structures can help minimize some of that management, but particularly the automated structures will add considerably to the cost. The potential impact on neighbors is something that needs to be considered both in the design and then also in the management of the system. And so, especially on a shared main situation, or if the topography is such that there could be an impact on the neighbors, then that needs to be accounted for in the management of the system, such that the management doesn't have an adverse impact on those neighbors. Another consideration would be then in the spring, as the boards are removed, not removing those in a way such that some excess flows downstream then could cause issues for neighbors. Since the primary goal of drainage water management is the reduction of nitrogen losses to the surface water, the impact of drainage water management on nitrogen should be a key consideration in developing the management plan. Drainage water management reduces nitrogen losses primarily through reductions in drain flow. A number of studies have shown that the concentrations of nitrogen in the drain water tend to be pretty similar, and so the reductions in nitrate losses then are generally proportional to the reductions in drain flow. There's some potential for increased denitrification within the soil profile. However, most of the water and nitrogen will end up leaving the field through some other pathway, either through lateral or deep seepage. This water and nitrogen that leaves through the lateral and deep seepage, though, then is a longer pathway than the shortcutting that would happen through the drainage system. And so that allows for additional opportunities for denitrification and assimilation or plant uptake as that water makes its way either to the stream system or down to deeper depths. Because much of the nitrogen will leave the field through another path, or what remains then is available for release as the boards are pulled in the spring, there's no real evidence that nitrogen applications can be lessened because of drainage water management. And so even with drainage water management, standard application rates for nitrogen should be followed. Since reductions in drain flow are the primary method for reducing nitrogen losses to the surface water, then the management plan should then be written such that drain flow is limited both in time and amount to only that which is necessary given the other constraints of the system. The potential impact of drainage water management on yield is one of the potential selling points of the practice. The positive impact on yield has been demonstrated in some years under drainage water management systems. However, that increase tends to be fairly modest, in the range of 1 to 5%. Potential for those increases in yield will happen in some years, but certainly not all years, and will depend on receiving sufficient rainfall at the right time of the year to be able to capture and store some of that water. The interaction of drainage water management with tillage system is another potential point of consideration, particularly in no-till systems, which tend to be cooler and wetter in the spring. The boards may need to be pulled earlier to allow for some additional warm-up. The impact of drainage water management on soil quality is an area that requires some further study. One area where drainage water management will work to improve soil quality is through reduced oxidation of organic matter. By maintaining an elevated water table at times of the year, then drainage water management will help in retaining organic matter in the soil. But the impacts of drainage water management on other aspects of soil quality is not yet known. Related to that, a common question is whether drainage water management will have an impact on earthworms. The short answer to that is maybe, but that's another area that requires further study. Certainly, excess wetness could have an impact on earthworms, but whether the wetness increase that occurs under drainage water management is enough to impact earthworm populations is something, again, that we don't yet know. In saline or sodic soils, the impact of drainage water management on salinity and sodicity adds another area of consideration in the management plan. Although the water table may be elevated at times of the year with drainage water management, drainage during the spring and other times of the year should generally provide enough downward flux of water to result in leaching of salts. However, where drainage is being used to reclaim saline soil situation, the producer may want to consider holding off on implementing drainage water management for a period of years until that lost production is, or most of all of that lost production is regained. Sodic soils require additional considerations in the context of drainage because of potential concerns about soil dispersion in those high sodium soils. Additional expertise in soil chemistry may need to be consulted in soils with high sodium absorption ratios. However, drainage water management may have the potential to help reduce the potential for dispersion by bringing calcium and magnesium ions back up into the soil solution at times of the year. Another common question about drainage water management is whether the practice might cause blowouts in the system. However, commercial control structures designed for drainage water management don't physically close the tile, but instead just raise the outlet elevation. And so when the water table reaches that elevation, it is still able to freely flow over the boards. Because of this, then excess pressure isn't built up in the pipe. If an actual valve is used to close off the pipe, then the potential for excess pressure heads is a potential, and so that should be either avoided or monitored carefully. There is some potential for blowouts in downstream mains if those mains are inadequately sized to be able to handle the discharge as the boards are pulled in the spring from the drainage water management system, but particularly if multiple drainage water management systems are all releasing water at the same time. The potential for tile plugging with sediment is another common question. While the stagnant water at times of the year when the boards are raised will allow sediment to settle out in the pipe, as long as the drains are placed on adequate grade, there should be enough flushing of that sediment while the system is operated in conventional drainage mode to prevent any sediment buildup in the pipe over a longer period of time. By reducing the amount of drainage, there is the potential for some increased runoff and soil erosion as a result of drainage water management. However, since drainage water management is most suited to fields with relatively flat topography, the potential for soil erosion is already limited on these fields. Nevertheless, runoff and any resulting erosion should be monitored carefully, particularly in the non-growing season when the boards are set high. If needed, then additional practices to reduce erosion or potentially changing the board settings to allow for some more infiltration may need to be implemented. During the conservation planning for the drainage water management system, then, it's also an opportune time to work with the producer to encourage them to adopt other practices such as conservation cropping or tillage and cover crops to minimize any potential for soil erosion as a function of the drainage water management system. Where manure is being applied to fields with drainage water management, the board should be raised for a period just prior to manure application and for some period after manure application to prevent the potential loss of nutrients from manure that may have found its way into the drains through macropore flow. Another topic of interest, particularly in the Dakotas and northern Minnesota, is the potential for drainage water management and control structures to reduce potential flooding in the springtime, particularly from snowmelt. The concept is that by draining out the system in the fall and then putting boards into the control structures just prior to snowmelt, potentially some of that water can be infiltrated into the soil and held back from releasing to the surface water and potentially reducing flood peaks during that springtime. However, this is something that has not yet been studied enough to know for sure whether this will actually work. And also it should be known that this is not yet covered under the 554 standard. In summary, then, the drainage water management plan should address both the production and the environmental goals for the system. Those goals, along with the desired level of management from the producer and other potential constraints for the system, should inform that planning process. And finally, since each situation is unique, drainage water management should be practiced in an adaptive management framework so that that drainage water management plan and the management of the system can adapt as necessary to best meet those goals.